All right, so now we're live. A couple of announcements. This morning I got the homework portal up and ready for use, and I also recorded a new video demonstrating how to do it. So the link is now live and the video is posted right below. And it's fairly self-explanatory, but I recorded the video just to sort of describe the system and walk you through it. So if you'd be willing to take about 2 minutes of your life and complete this, it's not a real assignment, it's just questions over the syllabus, just designed to give you some practice. And if you can do that by next week, I can give you 3 points extra credit, which translates into 3 free late assignments. Another thing that I learned in this process is that apparently YouTube has changed its default playback. All of my videos looked really blurry for some reason, and I was trying to figure out why, because that had never happened before. Turns out it's not my video, it was a default setting that made it play at the lowest quality. That way, in case you want to watch videos on your phone or something, it doesn't kill all your data. So I just thought I would point that out in case anyone else is seeing the videos and that they look really blurry, that is a setting on the video quality that you can either change per video or you can also change it as a default for whatever your browser, YouTube, whatever is using. So if you have problems with the systems, here's the login screen. Last name is whatever Maui thinks your last name is. So I say that because I know some people get married or they get divorced or otherwise things change. So if you are somebody who uses 2 last names, for instance, then you would enter both of them with a space or with a hyphen, whatever you have it officially registered as. If for whatever reason you can't get through using your last name and your 8-digit Iowa ID, let me know and I'll see if there's a discrepancy in what you think your name is and what my system thinks your name is. So I stole everything directly from Maui. So when you get a chance, please play with that and let me know how it goes. All right, deal? Yeah, we can do that. Within the next week, it won't take you very long. Let's see what else is up. Nothing else is up from last time. I've got all the videos from last week recorded. We're ready to pick up on lecture 1, so let me grab that. Here, let's do a little question and answer. We'll give you something nicer to look at. Something much nicer than what the view is currently outside my window. I hear that there's more snow coming and possibly a flash freeze on Thursday, so that'll be fun. I tell you, if we get any more snow, we're not going to have a mailbox at my house anymore. The piles are like literally up to the top. It's anymore, and there's not going to be any mail. But anyway, we'll look at the pretty beach instead. Tell me what you remember from last time, please. As usual, I will take words, gestures, typing, whatever you feel like.
I think some of the difference between SAS and stata and capitalization and how you stick it to the man at times.
That's what you remember. Okay, all correct. Yeah, so in the videos that I recorded, sort of walking you through getting started with SAS and stata, I go through the syntax and try to talk about the language. But yes, SAS is not case or space sensitive for the most part. Stata is. So in stata, it makes you write everything in lowercase for the stata commands, whether you like it or not. And so, yes, I stick it to the man by referring to stata in all capital letters whenever I possibly can, just, to be ornery. Yeah, so one of the big differences in terms of the syntax that you'll see throughout this example is that in SAS, you have to refer to which database you want to be pulling information from when you're asking for it. And then in stata, you don't. So the stata code is always going to be a little simpler. Good. What else?
I remember Stata had less typing and SAS, had more, and you always had to use the semicolon.
Yes, semicolons are a thing in SAS. They are how SAS understands that you've finished a statement. So in stata, you've finished a statement when it goes to the next line. So semicolons are a big deal, as is the word run. So we have proc whatever your commands, and then the end of the statement is run. And that's like adding the please onto the end to make sure that it actually goes. What about variables? We were talking about kinds of variables that we'll be interacting with. Two main kinds. You remember?
Was it the continuous variables?
Quantitative, yeah, continue-ish. That's one kind. That kind of variable is a number is actually a number. So it's an amount of some kind that you can interpret as a number. Interval measurement would be the terminology that goes with that. What's the other kind?
Categorical.
Categorical. Synonyms for that?
Qualitative.
Ordinal?
Qualitative. Ordinal is one kind. Yeah, so within categorical variables, we have binary when there's just two choices, ordinal when there's more than two and there's a natural ordering, such as in Likert scales or rankings, and then there's nominal when there's no ordering. And so, yeah, if you hear the term qualitative variable, categorical variable, factor variable, grouping variable, I'm trying to think, those all mean the information might be stored using numbers, but the numbers are not numbers. It's like 1 means this, 2 means this, 3 means this. And that's how I would recommend storing that type of information, because people can't screw up typing 1, 2, or 3, but they can screw up spelling words out and making sure that they have the right capitalization in the process. So yeah. We started talking about describing those variables. So if I wanted to say in a method section, describe a categorical variable that I had collected, what would I need to tell people?
Is it like the frequency tables and plots?
Yeah, frequency, just the count of the responses in each possible category. And to make that a little easier to understand, we usually convert that to a percentage. So percentage would be like 45.6. Proportion would be 0.456. The latter is how the homework system will ask you to enter that information in your first assignment. Not due for a while, but just as a foreshadowing there. We make frequency plots, bar graphs to try and describe that. What about quantitative variables? 3 salient features we started talking about, and we've gotten through 2 of them. What do you think?
I'd say central tendency and spread.
Yeah, I think the word I used is dispersion, but spread works as well. So if you have a numeric variable, people usually want to know where's the middle at. So what is like the average score, so to speak, and then what is the dispersion or spread around that. So yeah, you'll see me do this sort of gesture to indicate that. 3 measures of central tendency that you probably remember from grade school. Mean, median, and mode. We'll talk more about when those would be the same versus not the same today. And then for dispersion slash spread, what would we use? A few new words.
Variance and
Standard
standard
deviation.
deviation.
Yeah, how are they related to each other?
Variance square is standard deviation. Oh, sorry, it's the opposite. Yeah,
Other
so
way
the
around. This
square
is
root
why I
of, yeah.
asked it. Yeah, so we compute the variance as how far off each case is from the mean. Square that. That way the positive offnesses and the negative offnesses don't cancel out. Sum that, divide by n minus 1. And so then that describes the average offness from the mean in squared units, which is not very useful because nobody thinks in squared units. And so then we can take the square root. We took a vote on that, decided it was root, and then that describes the average deviation of any one case from the mean. So that's a common way of indicating spread or dispersion. Descriptively, people tend to use standard deviations when we get to models and we talk about sort of how much information is being captured by the model relative to information left over. We will phrase information in terms of variances instead of standard deviations. So it's good to keep in both of them in the back of your head. I think that's about where we left off. That sound about right? That's my recollection anyway. Any questions or comments before we jump back in? No? Okay. Then away we go. So we talked about central tendency, we talked about dispersion. Interquartile range is another way that people will indicate dispersion, particularly for variables that are sort of funky looking, that don't really come from a standard distribution. Let me see where we are. we started, and I think this is about where we were going to pick up. So this is slide 14 of lecture 1. So starting to introduce a little more vocabulary and terminology to go with these ideas of mean, variance, and standard deviation. So in general, whenever we talk about a quantity that is being calculated or estimated, by the way, I'm going to say the word estimated a lot. That just means a way of finding the number. So in these examples, we have a formula that works to find the mean, right? It doesn't matter what kind of variable you have, you can find the mean with that formula. But later on, there aren't always going to be ready-made off-the-shelf formulas by which you can find things. And so you can use the word calculate when there is a ready-made formula, but when the answer can't be found that way, when you have to sort of iteratively search through a set of answers and then decide which one's best, which is what happens in advanced models, the term for that is estimate. So you will hear me say that, but just know that it's just a way of getting the answer that you're interested in. So anytime that we're trying to estimate something in a sample, like the mean of a variable, like the variance of a variable, we would call that a statistic. But the reason that we're trying to do that, usually in research, is to try and get some sense of what that quantity would be in the population that we care about. And so the term for that quantity, the thing that we actually care about, that we're trying to represent with just one sample, that's parameter. So parameter is like the thing we're trying to find. Our version of it in one sample is called a statistic. And so then to make that distinction, we have different notation that goes with the idea of what it's supposed to be in the population, the parameter, versus what we have in our one sample. So for instance, for the mean, which in a results section, you would just abbreviate with a capital M, that is indicated by this Greek letter right here. Do you see this U looking thing? I'm not good with Greek letters. I'm going to be honest with you. Gun to my head, there are certain ones that I still don't know. Like there's one that I call squiggle 1, and then there's squiggle 2. I'm not even sure what their actual names are because that's what I've named them in my head. I will tell you that in my classes, I only use Greek letters that I can draw reliably with a marker. That is my criterion. And squiggle 1 and squiggle 2 do not fit that criteria. But I can't do this one. This U looking thing is called mu, and that is Greek for what our population mean parameter is supposed to be. So anytime that we try to get a mean, we're trying to actually get that one. Our mean that we have in a sample is what we had last time, this quantity y bar. So I will tend to use x's and y's as names of variables. Y's are going to be outcomes and x's are going to be predictors, but that distinction isn't yet relevant, but that's where y comes from. Variance then, so you will see VAR as an abbreviation for that in stats packages and sometimes in method sections as well. The variance of the population is this thing right here. This is sigma. And because variance is in squared metrics, it's how far off from the mean you are on average squared. We have the sigma squared sign to remind us of that. In any one sample, it's S squared. So then you might imagine, well, if variance has the squared on it, standard deviation, which is the square root of that, is then just sigma or S. By the way, sometimes people report something called a coefficient of variation, which is a standard deviation divided by the mean. I honestly don't know why. That quantity to me does not seem useful. But just in case someone ever asks you for it, there you go. So those of you who've had some version of intro stat before, some of these probably look familiar, yes? This is something that people make a big deal about. To be honest, when I was in that position, I didn't see the point of why we needed different letters for the same idea. Like, who cares if it's mu or y bar? It's a mean, right? The end. I now understand a little more why there's a difference, and so hopefully I can convey that rationale to you as well. The third salient feature of a quantitative continue-ish variable, though, is asymmetry, and that is a quantity known as skewness. And skewness refers to how far off the middle most of the information is. And the way that skewness is named is intuitively backwards from how you think it is. So for instance, this distribution over here on the left, we would characterize this as positively skewed because it's where the tail goes is the way that it's named. So this can result anytime that we have a quantitative variable that has a lower boundary. For instance, count variables where you can't go below 0. If the lowest you can have is 0, sorry, I got to go this way, that can cause sort of a pile up on the low end, and then you would have a tail going off into the positive direction for people who have very large counts. A distribution that lacks skewness, that is symmetric, or symmetrical, as this person wrote, is the one in the middle. And this is sort of a classic, what's known as a bell curve or a normal looking curve. We'll talk about that, I think, either today or next time. And the negative skewness is on the right here. And so just like positive skewness can result from a boundary on the lower end, negative skewness can result from a boundary on the upper end. For instance, this is my hopeful grade distribution at the end of the semester for you. Big pile up on the high end. Very few, if anybody, on the low end. So when there's an upper boundary that you can't go past, such as in percent correct or something like that. The way skewness is calculated is the deviation between each individual variable value, so y sub I, y for each individual, minus the mean to the third power. So that's where sometimes this is known as a third moment of a distribution, is its skewness, and there's also a fourth that's coming later on, but that's where that terminology kind of comes from. One thing to note about measures of central tendency: if the distribution is symmetric, mean, median, mode are going to fall pretty much onto the same value. It's when the distribution is asymmetric or skewed that you get different answers for mean versus median versus mode. So a ready example would be something like home prices. So if you're looking to move somewhere and you go to like cost of living indicators, one of the things that they're probably going to tell you about is the median home price, right? It's always phrased that way. And this picture kind of illustrates why that might be. What's the lowest amount of money you could pay for a house? Well, 0 in theory, probably something above that, right? But what's the most amount of money you could pay for a house? A gazillion dollars, right? There is really no ceiling. And it really depends on where you live, what that ceiling is. I remember when I got my first real job and I bought my first house, and it took 3 mortgages to do it, which is probably a sign that it was out of my budget, but I was very proud of it. It was in Lincoln, Nebraska. And yeah, I was just coming out of school. I had no money, right? But I had a job now, which meant I could get a house now because the bank was like, well, you got a job. I'll give you a house. It's fine. But anyway, I went on a business trip to San Francisco. I was doing some statistical consulting with a group, and they invited me to come visit them. And I went for a walk with the person I was staying with around her neighborhood, found a house that fit my house pretty much the same in terms of like the square footage and the bedrooms and stuff, except it was $1 million more. No joke. So yeah, house prices, good example of a positively skewed distribution. And so because high values can pull the mean towards sort of out of the bulk of the distribution and towards the tail, medians can be a better, or I would say more robust version of central tendency because the median and the mode are going to be closer to where the bulk of the data is. By the way, a synonym for median is 50th percentile. It is literally the middle of the distribution. So this is cough, cough, homework question. You can tell what the shape of the distribution is going to be by the discrepancy between these 3 things. So if the mean is higher than the median, odds are good the distribution is positively skewed. If the mean is lower than the median, odds are good the distribution is negatively skewed. So the median is going to be closer to where the bulk is than the mean. Okay, with me? Okay, all right. So in the example data that I'm playing with for example 1, again, this is from the General Social Survey, and the variable that we're looking at is income in thousands of dollars annually for one person. And this ranges from about $200 a year up to about $69,000. So I computed, meaning I asked SAS and Stata to compute. Whenever I say I did this, that's what I mean. The program did this. I don't do math. I'm actually pretty bad at it. Mean is about $17,000, $17,300. The median, though, is only $13,000. So the median is less than the mean, and this distribution would be what kind? Do you think this is positive, neutral, or negatively skewed?
Positive.
Is it
Yeah,
positive?
this is positive. Yep. It's where the tail is, not where the data are. I know it's not intuitive. There's going to be a lot of things in statistics that are named badly or phrased badly, and we just have to handle it. Just have to deal with it. Mode is $22,000, and so in this case, the mode is the most popular value is actually heading into the tail. If we have standard deviation of 13.79, that means the square of that is 190. And the interquartile range in here is the difference between the 25th percentile and the 75th percentile. And so that's another way of characterizing standard deviation. It's characterizing dispersion, I should say. Standard deviation is one measure, interquartile range is another. So generally speaking, you'd want to report mean, standard deviation, minimum, and maximum. If you have a variable that is asymmetric like this, you might throw in median and interquartile range as well for descriptive information. You might make a picture like this. So this is a picture called a box plot. And I have been asked for such things rarely, but I wanted you to see it because this is one of the things that people use to describe quantitative variables that are not necessarily well behaved. So this is the same histogram in which we have bins of $5,000 in here as a box plot. And so this shows where the bulk of the data is. The median is the line, the mean is the diamond, and then it has minimum and then sort of these different descriptions of percentiles. So the box itself is the interquartile range. There's some definition of an upper fence that the program uses to denote sort of where the outliers start, but all these guys out here are outliers, meaning that they are sufficiently far away from the mean that people are like, whoa. So outliers can be in a good way, and outliers can be in a bad way. The question that you always want to ask yourself, though, is, are these observations believable? Because there is sort of a bad reputation of what's known as data cleaning in statistics. Have you heard this phrase before? Or data transformations? It's the idea that we should make our variables look well behaved. And so these guys that are dragging everything sort of to the right gotta go. So some folks would encourage you to remove them because they're outliers and we don't want them to have undue influence on the solution. That should make you nervous anytime that you're messing with your data, because how do we decide what is really an outlier? Is it all of these cases or just like these three? And are these people who would actually be part of the population, or are these outliers for some other reason? That's what you'd have to ask yourself. And if the values are believable, I think they stay in. So it turns out that there are techniques designed to analyze data that have outliers. You don't have to get rid of them, you just have to learn those techniques. So if you've heard of linear regression before, that's something that we're going to do in this class. There's something called quantile regression that you can do instead. Linear regression is all about predicting the mean, whereas quantile regression is all about predicting the median or any other percentile. So you can change the model to fit the data. That should be one thing that you take away from this class, is that there is no single right model. It's right for whatever you are facing. By the way, these plots have gotten fancier. You might see the term violin plot that goes with this, and it's kind of like a box plot on steroids. There's more stuff in it, but it's meant to sort of convey the same information. So how did I get all these numbers? PROC univariate. So in SAS first, and then we'll do Stata, there's about 17 different ways to get a mean, right? We did PROC means last time because it gives you a nice, quick little table that has some basic shit in it. If you want to know more than that, PROC univariate would tell you basically everything you want to know about a variable. So to review, PROC stands for, do you remember?
Procedure.
Procedure.
Yeah. And univariate doesn't stand for anything, it's just a word. Data equals, so you're telling it what the name of the data set is that you want to pull information out of. Work is where it's stored, so a directory that SAS recognizes is named work. The name of the data set is example 1, semicolon. Var means which variables or which columns in the data set you want the information for. Income is the name of the column, so this has to be spelled correctly in SAS, but it doesn't have to be the right capitalization. You can type lowercase or uppercase, and then run also with the semicolon. So when you see SAS code from me, SAS dedicated commands are always going to be in capital letters. Things you would change are going to be in either lowercase or title case, as it's known. But if you run PROC univariate, you get these 3 tables, and you can get a whole bunch of other stuff if you want that has skewness. There's your coefficient of variation, variance, kurtosis, which we'll talk about in just a second, as well as all of these quantiles. And it labels it for you that the 50th percentile is the median. Stata gives you all of that stuff for the same command that we had last time, which is just summarize. Remember, in Stata, you don't have to list the data set. It only has one open in memory at a time. Income is still the name of the column. The comma is used to denote an option. So like, what do you want it to tell me about income? And the option detail is used to give you similar statistics to PROC univariate, such as the percentiles, the median here, the variance, skewness, and so forth. So this is the kind of thing that I'm going to have you do for your first homework, just to kind of get used to working with SAS and Stata, be able to get it to spit out this kind of information. Fourth salient feature of quantitative variables that I want you to have heard of and then forget about is kurtosis. Kurtosis refers to how much narrower or flatter the distribution is than expected. In practice, it's nearly impossible to tell it apart from variance, and it's not something that we would typically worry about. So this is just an example. A distribution that is more peaked is called leptokurtic, and a distribution that is flatter is platykurtic. And that's the only way that I remember that, is because it's like flat is plat. So it's a nice mnemonic that way. I never remembered this word though. So you've seen it. It's the 4th moment because to calculate kurtosis, it's each individual observation minus the mean to the 4th power. So we won't worry about that too much. So central tendency, dispersion, and skewness are all things that apply to quantitative variables. You might ask yourself, well, do I need to worry about those things for categorical variables? And in short, the answer is no. Frequency is it. So for instance, if I had a variable that is nominal, so this is marital status, where people were given 5 choices and they answered in 1 choice. This is the distribution of the percentages. And you'll note that 1 is coded for married, 2 is widowed, 3 is divorced, 4 is separated, and 5 is never married. I asked SAS and Stata to give me a mean for this variable, and they were happy to do so. The mean for this variable is 2.74. So what the hell does that mean? Does it mean most people are divorced? Like, because that's where it's closest to 3? Does this make any kind of sense to have a mean for this variable? No, they're not numbers. Means and variances and skewnesses are things that have to do with numbers, and this is not a number. Now, I'm making the point, though, that if you ask SAS or Stata to give you the mean for this variable, they're happy to do so. So the programs do exactly what you tell them, which is both good and bad, because the onus is on you to tell it to do something that makes sense. You will see means calculated and reported for ordinal variables, like 1 equals strongly disagree, 2 equals disagree, and so forth. That's more okay, but still kind of weird, because they're not really numbers. But if I had a variable that was scaled from 1 to 5, and I had a mean of 2.7, then I would say the average person is somewhere between disagree and neutral, which to me is like, okay, that kind of makes sense, but it should give you a little bit of pause because they're not really numbers, even though people will treat them that way. In terms of variance and skewness, so if I have a binary variable, for instance, that's the one circumstance in which a mean makes sense. So if I have a binary variable and they are almost always coded as 0 versus 1, like to begin with, and that is the most convenient representation because if I have a mean, that gives me the proportion of observations who have a 1. So if the mean is 0.6, I know that 60% of the cases got a 1, that means 40% got a 0. So a mean is okay for a binary variable. We can pretend like it's a quantitative variable for all intents and purposes. But it turns out that once we know the mean for a binary variable, we know the variance and we know the skewness, because they are combinations of the mean. To be more specific, the variance is the proportion of people who got a 1 times the proportion of people who got a 0. So that means if you have a variable that's split 50-50, for instance, the mean is 0.5, the variance is 0.25. And you'll note that the variance decreases as you move on either side of that. So the closer you get to it being a constant, the less variance the variable has to have. So if you have a binary variable, you don't have to worry about thinking about its variance or thinking about its skewness because it's determined by the mean. This will have implications for how one would have to predict a binary outcome differently than an outcome that has more variability in it that's actually quantitative. That happens in a subsequent class if you're interested in learning how to predict binary outcomes. So percent or frequency is enough to report for these. So there's our intermediate summary. If we have a variable that's a number, we want to know some kind of central tendency. Mean is usually the standard, median if you think it's skewed, and the median would be helpful in addition. Some kind of dispersion, so standard deviation is going to be the big one. How far off on average each case is from the mean, and then indicate whether or not it's skewed, positive or negative. If you want to make a picture, histograms are good pictures, Bach plots or violin plots. And then for categorical variables, really it's all about the percentage in each category, and that's all you got to worry about or plot. So, how are we doing? Okay. So the point of gathering this sort of information in a sample is to try and say something about the population the sample came from. To do that, though, this information that just describes the one sample has to be expanded. We need to know something else that is going to tell us about how inconsistent each of these numbers would be across repeated samples of the same kind. So if I told you that the mean is 5, would you expect another sample of the same size and the same kind of people to have a mean of exactly 5? If I redid the study, if I did a replication, would I get a mean of exactly 5 again? Probably not. You hope it'd be close, like 4.8, 4.9, something like that. So that idea of how much inconsistency would we expect in these values, the means, the standard deviations, and so forth across samples, that allows us to make some sort of inference about how our sample would compare to other samples, and then eventually try and get back to the population. So we're talking about switching from just describing a variable to trying to make inferences about the variable, trying to extrapolate beyond just the sample that we have at hand. And to do that, we have to be able to characterize the expected differences across samples using some sort of statistical distribution. So the term for this is probability distribution. There's probability mass functions or probability distribution functions. The idea, though, is that this is our guiding principle as to how the same information taken from different samples is expected to differ from each other. So this is going to be one of our new friends. You seen a picture like this before? I stole it from Wikipedia. This is our new friend, the normal distribution. It's also known as a Gaussian curve. Apparently, Gauss was a mathematician who is credited for developing it, although I heard a story recently about how other people came up with it before him in a whole separate country in a separate decade, but whatever. Normal curve, bell curve. This thing is going to turn out to characterize how different our sample statistics are from each other across samples. So this distribution is an example of one that has no skewness. It's supposed to be symmetric. And there's only two things you need to know to be able to characterize the distribution and predict the expected, what this y-axis is likelihood. You can think of it as probability. It's close enough conceptually. All we need to know is the mean and the variance. If we know that, then we know how likely any value is given this distribution. So for instance, if I look at this blue line versus the red line, they both have the same mean. The mean is 0 in both, that created both of these lines. But they differ in their variance. So the blue line has a variance of 0.2, which is less than the red line's variance of 1. So that's why the blue line is taller. It's less spread out. It's less dispersed. So the mean and values right around it is a lot more likely in a distribution that has less variability than the red distribution that has more variability. So it's like how certain you can be that the mean is like that's what we can expect for somebody. You should take into account the variance around it in making those sorts of expectations. I'm going to go with the goldenrod. Can I get a vote on that? Sort of this dark yellow. Going to the 64 pack of crayons. Goldenrod is some final answer. That one also has 0 saffron. Ooh, okay. Came to play. I'll take saffron. That one has a mean of 0 and a variance of 5. So now at this point, it's like, if you think about the mean as like the most likely middleness, it's like, not so much, right? There's enough variability around there that it's like, yeah, 0 is the middle, but it's not a good middle. And then we got green over here, which has a whole different mean. So the idea is that if we know the variance and the mean, we can figure out how likely any one value is. So let's say that I have, let's go with this value of -1 right here. The y-axis tells me how likely that value is given the distribution that it came from. So it looks like a value of -1 is most likely to have come from the red distribution or maybe the green. They're kind of tied at that point. Whereas a value, say, of 3 is more likely to have come from the yellow distribution than the other ones. So the role of these probability distribution functions is to give us some sense of how likely any given result happens to be. And by the way, here's the formula that created these lines. This is actually one of the more complicated distribution formulas. I don't have it memorized. I teach this stuff for a living and I don't have this memorized. It's fine. So we're going to use the normal distribution to talk about our mean and how our sample's means would compare to other sample's means. So to be able to make an inference then, like I said, we have to find some way of indexing the precision of our mean or its expected consistency across samples. The way that it's actually phrased, though, is inconsistency. It's by a number where higher values indicate more differences across samples of the same kind. So just to illustrate this concept, we'll start with just the mean for our sample and ask the question, okay, how different is our sample mean from what it's supposed to be? So in research, we don't often know what things are supposed to be, but there are certain situations in which we do. For instance, here's my trusty Diet Mountain Dew can. I know how much caffeine and liquid is supposed to be in this thing. It's 12 fluid ounces. So that is an expected value, right? So if I were a scientist who wanted to potentially disprove my hypothesis that Mountain Dew has good quality control, I could pour out my drink and measure it. And so I have an expectation for what it should be, and I have data for what it actually has. So there may be situations like that. So like if I had a whole 12-pack, I have a whole 12-pack of cans, I could pour the liquid out and compute the mean for each across the 12-pack and see how close it is to what it's supposed to be. So that's the kind of idea that we're starting with just as an example. So if we know what the population mean is supposed to be, so that's the mu here, how likely is it that we found the mean that we found for our sample? That's the question that we're going to try and answer. So what's going to affect how close any one sample's mean is from the population mean that it's supposed to be, that we would expect it to be, is going to be two things. So to illustrate this process, I'm going to play God. All right, I'm going to do what's known as a simulation. I am making up data. So I created 100,000 fake people using a normal distribution, and I gave that distribution a mean of 10 and a variance of 25. So within my sample of fake people, the average person is off by 5 on average relative to the mean. That's what a standard deviation is. So the middle, the mean is 10. Any one individual is going to be off from that mean by an average of 5. 5 squared gives you your variance. And here they all are. So the nice thing about fake people is that they behave perfectly. That's why we don't have real people. Okay. And turns out, yeah. So the blue line is what is expected for this distribution, and the red line is what I got. So my actual mean of these 100,000 people is 9.98, and my actual standard deviation is 5.01. So yeah, with enough people, it's pretty damn close. So what if this is truth, right? I know this is my population, and I want to simulate what it would be like to do research. So I'm going to draw out a bunch of people, compute their mean. Draw out some more people, compute their mean. And do this over and over and over again to try and show you what happens as a function of two things. One of them is going to be sample size. So this picture here on slide 29, these are histograms, but they are not people. They are samples. So if I took my population of 100,000 fake people, drew 5 people out of it, computed their mean, drew 5 more people, computed their mean, and I did that 1,000 times. This picture on the top left is what it looks like for the distribution of the means from each sample across samples. So I'm trying to say this slowly because this is a different thing. In quantitative methods, we have to talk about two different levels of abstraction simultaneously. There's the sample, so people relative to the mean and the distribution across people. But then if we take a summary of that sample, it has a distribution across samples too. So these pictures is the distribution across samples. That's what we're talking about. So if I only have 5 people in any one sample, what that sample mean happens to be is really noisy. So this picture here is centered around 10, but any one sample could have a mean all the way down to like 5 and all the way up to 15. So there's a lot of variability in what you would get from any one sample if you only had 5 people in it. If I had 10 people in it, a little less variability, but not much. 15 people, getting a little better. 20 people, 30 people, 50 people. So the point of this is that the larger your sample, the less inconsistency you would expect across samples in what the mean would be. So more people should give you a better estimate. More people should give you a sample mean that is closer on average to the population mean it's supposed to be. More makes it better. So the term for this idea of how the characteristic of any one sample would vary across the same kind of samples if you did it over and over and over again, this is called a sampling distribution. So what these pictures are showing is the sampling distribution of the mean specifically. So these aren't people, these are samples. So I calculated what the mean and standard deviation of these samples is. So this is the mean, this column right here on slide 30. This is the mean of the sample means. And good news, it's 10 like it's supposed to be, because fake people very well behaved. But in any one sample, how likely are you to get the right answer? That depends on how many people you have. So this column on the right here, this is the standard deviation of the sample means, meaning how far off on average any one sample mean is from the population mean. And it gets smaller the more people are in your sample. So your sample mean is going to be closer on average to the population mean if you have more people. So people, the number of people in your sample, that's one thing that's going to create inconsistency across samples. More people, less inconsistency. The other thing is how spread out the people are. So how good is the mean from any one sample is partially a reflection of how much dispersion there is around it. More dispersion, more inconsistency. So I made, this is the same picture from before. This is a new sample of fake people where the mean is still 10, but now they have a standard deviation of 3. So these are people. These histograms are the 100,000 people. On average, any one person is off from the mean by 3. So that's mean and standard deviation of a sample. Now, what do you think is going to happen if I make samples out of this population? So grab a sample of 5, get the mean. Grab a sample of 5, get the mean. The same tendency across sample size. The more people in a sample, the tighter the distribution around what the sample mean is, the better, the more consistent any one sample mean estimate is going to be. If I compare what happens for standard deviation of 3, though, versus standard deviation of 5. So this is 5 people, 10 people, 15 people, and then the top row is if there's only a standard deviation of 3 in the sample versus standard deviation of 5. And so if the people are closer to each other in your sample, the means across repeated samples are going to be closer to each other also. So more people that are more the same means your sample mean is going to be closer to the population mean on average. So, is this shit crazy or what? We only have one sample, usually, right? But I'm playing God here with the computer. I am making up fake people, I'm making fake samples to show you that even though we only have one sample, people way smarter than me who do math figured out that we can use the information from just that one sample to anticipate what would happen across repeated samples in a population, even though we don't have any of that. Welcome to our new friend, the standard error. So this is a new quantity to add to our list of vocabulary. We have mean, we have standard deviation, and we have standard error. So what we are talking about is a quantity known as standard error of the mean specifically. Any statistic can have a standard error. And it describes for a sample how far off on average any one sample mean is going to be from the population mean. And to make it, all you have to know is the standard deviation of the population and your sample size. In practice, we don't usually know what the standard deviation is of the population, so we swap out the one for the sample and try to call it good. So this is a level of abstraction higher than standard deviation. This can, right? If I were to talk about how far off this can is relative to the other cans in my 12-pack, that's standard deviation. If I took the mean of my 12-pack and compared it to the means of all the other 12-packs still sitting on the shelf, how far off my 12-pack's mean would be on average from what it's supposed to be in the population, that's standard error. They sound kind of the same, but they refer to different levels of abstraction. Standard deviation is how far off a person is on average from the sample mean. Standard error is how far off a sample mean is on average from the population mean. And that's what allows us to make some sort of conclusion about whether or not we're too far away from what the population mean is supposed to be, or whether it's within some sort of acceptable fluctuation. Standard error controls what is acceptable. So the more spread out your people are, the higher your standard error. The less close, the further away any one sample's mean is going to be from the population mean, but the more people you have, the closer it is. So more variance makes standard error go up, more sample size makes it go down. So here is proof, and I don't use that word lightly, because in science we never get to say proof, but in math you can. So this is a demonstration that if we compute the standard errors I just described, standard deviation over square root of sample size, these numbers that we computed from just one sample are pretty damn close to what you get if you actually do the repeated sampling. So the standard error that comes from one sample is supposed to approximate what would happen if you did the same sample over and over and over again. And the approximation is better if you use the population standard deviation than if you use the sample one. Sample one is going to have more inconsistency to it. The smaller you have, the smaller your sample size. Okay, how are we doing? I'm seeing some frowns, some concentration faces, I should say. That's okay. This takes a minute to get used to the terminology and what we're trying to do. So where we're going with this eventually is to try and make some sort of decision as to whether or not what we found is too weird relative to what we expected, too discrepant. And in order to answer that question, we have to have some kind of index as to what expected fluctuation would be, to know if we're beyond that or not. So standard error is a way to describe what is expected noise. How far off is the sample mean from the population mean on average? Okay, that's kind of like expected noise. Now, where do we fall relative to that? That's the question. So it turns out that you don't have to have data that look like that normal distribution for this to work. The idea that the more people you have in any one sample, the closer the sampling distribution of the mean gets to normal. So we're talking about these pictures. Go back. This picture right here, the more people you have, the closer to normal it looks. That thing is called the central limit theorem. And this is a point of misunderstanding for, I would say, students and actually some people who teach this stuff. The central limit theorem does not say that if you have enough people, all variables look normal. That is not what it says. It says that if you have enough people, the mean of a sample across repeated samples, the sampling distribution of the mean, that thing looks normal. And that's why we can use statistics to make conclusions about whether any one case looks too weird relative to what's expected. To prove it, to demonstrate it, I'm going to create a new set of fake people. So this is a new variable, 100,000 fake people. The distribution that I used to create this shape is what's known as a Poisson. Apparently that is French. Any French speakers in the house can verify? Nah. Yeah, I took Spanish, so this can't help me, but I know Poisson because I know this distribution. It's a classic distribution used for count data. And in this particular distribution, the mean and the variance are supposed to be the same. So there's a one-to-one correspondence. So you might have a distribution that looks like this, say for, I'm going to go with number of times I have to tell my child to stop talking, pull up his pants, flush the potty, and wash your hands before it actually happens. Because he just wants to share. He wants to tell me about everything. And so he's going to the bathroom and he stands up and he keeps talking and I'm like, no. Huey, pull your pants up, flush the potty, and wash your hands. And then you can finish your story. On average, 2 or 3 times before it actually sinks in that he needs to pull his pants up, flush the potty, and wash his hands. But on a bad day, it can take 7 tries. So, count distribution. So if you looked at this shape, would you say that that thing looks normally distributed? Does it look symmetric? Exactly. Is it positively skewed or negatively skewed? And feel free to read from the screen. Yeah, positively skewed. Lower boundary. Can't have counts that go below 0. The best case scenario is that I don't have to say anything and he finishes his bathroom transaction. But that doesn't get any better. So this variable is a count variable. It is not normally distributed. But I can calculate the mean for samples of different sizes and do that repeatedly. And here's what I get. So the sampling distribution of the mean, the set of means from repeated samples of the same kind, even though they're drawn from a variable that's not normal, start to look normal if you get enough people. Doesn't matter what kind of variable it is. It happens faster for some kinds of variables than others, but this principle still holds. And so that's why I said our new friend is the normal distribution, because that thing works no matter what kind of data we're talking about to be able to describe how different what we found for one sample is from what we expect to find in the population. And here's the standard deviation computed for each of these distributions, and here's the standard error of the mean on average for any one sample. And damn, it works. Math, who knew? So this took me a long time to believe, like philosophically, that I can just get one sample of people and that's enough to talk about like what it should have been in the population and what I would have got if I had more than one sample. It is enough. In certain cases like this, it is. That's not always true, but it is for something like a sample mean in this sort of independent samples. So we have the standard error of the mean here. How far off, on average, any one sample's mean is from the population mean. We can get that from our data as standard deviation over square root of n. But this idea of a standard error is more general than that. And so we will see several instances of this throughout the semester. In general, the standard error means how far off on average the sample whatever is from the population whatever, where whatever means parameter. So right now we're talking about how far off on average the sample mean is from the population mean, that's standard error of the mean. But we could also do this for the variance, like how far off on average is the sample's variance from what the population's variance is supposed to be, or the skewness, or the median, or anything else that we can make out of one sample. So standard error, our new friend, to be able to talk about what would have happened, even though we don't know for sure across repeated samples. So we can use the standard error to build some sort of range of uncertainty. It's like, okay, so like what should the mean be? Like what's the realm of sort of expected noise? And that thing is called a confidence interval. To build this, we have to make two decisions. What sort of distribution characterizes the behavior of the sample statistic? So across repeated samples, what should that look like? Is normal good enough? For now, we'll say that it is. We're going to make friends with some more, but normal's good enough for now. And then how confident do we want to be? We have to operationally define what expected noise is, meaning that we would find the population value 95% of the time, or 90% of the time, or 99% of the time if we want to be really confident. So the idea of confidence level is always phrased in terms of like a positive number of like 95% confident. The opposite of that, so like your unconfidence level, if you will, inconfidence. Can I get a judge's ruling? A confident? D confident? I'm going to go with unconfident, although that sounds wrong to me for some reason. Like unpretty, you know the TLC song? No? 90s people? No. Okay, look it up. The group is called TLC. They have a song called Unpretty. It's a nice little song. Anti-confident. Ooh, that's a good one. Yeah, so whatever unconfident is, the 5% that you'd be left with, that's called alpha. So that will have a special meaning to us. It's like, okay, how often are we willing to be wrong about this? That's alpha. Lack of confidence, anti-confidence. Confidence is how often we want to be right. So here's our distribution. We're going to use this thing to characterize the expected wiggle, inconsistency, offnesses of any one sample mean relative to the population mean. We're going to use this to characterize that. But this is not as helpful unless we have the same distribution sort of to refer to in a standardized way. So we're going to do exactly that. We're going to take this thing and standardize it, meaning we're going to force it to have a mean of 0 and a standard deviation of 1. And that creates something called the standard normal distribution, which uses the letter Z on the x-axis to describe it. So here's our new friend, standard normal. This is what we're going to use to start with to describe the behavior of a sample statistic like the mean. So we know that if something follows this distribution, then about 68% of the observations are going to fall somewhere within -1 standard deviation and +1 standard deviation. We know that about 95-ish, 96% of the observations are going to fall within 2 standard deviations, and 99% are going to fall within 3. And so then we can convert sort of how frequently we expect something to happen into this x-axis down here, which is called Z. And so you will get these numbers that you will see here that define these cutoffs. So if you want to have something happen sort of 90% of the time, that corresponds to a Z value of plus or minus 1.65, which is the green here. 95% of the time would be the light blue, and 99% of the time is going to be the purple. So the point of this is to be able to predict how often something would happen if we know where it came from. That's what we're going to try to do. So for instance, if I have my population of 100,000 fake people, I know what the right answer is because I made the data, I played God. I draw one sample from it, 50 people, this is what I get. So that one sample out of my population, this is the draw from, by the way, this gesture here, that's what it's supposed to mean. I'm literally like drawing balls or something out of an urn. There's a classic stats joke for you. The mean for the sample that I happen to get is 10.98. What's it supposed to be? And feel free to read from the screen. 10, yeah, see, I like answers that we can do with hands. It's a very like Zoom friendly kind of situation here. Yeah, I made the data. The mean's supposed to be 10. Well, I drew a sample of 50 people and I got 10.98. Is that weird or is that okay? Well, it depends, right? We got to find some way of defining what weird is. Well, I got a standard deviation of 4.6. It's supposed to be 5, so there's a little less variability. So this one sample is a little to the right in terms of the mean, and it's a little like narrower than what it's supposed to be. I can use the sample standard deviation and my sample size, plug that into my handy dandy little formula, and that gives me a standard error. So if we look at these numbers, 4.6. 4.6 is the standard deviation, which means it refers to people. In my one sample of 50 people, any one person is going to be off from the mean on average by 4.6. Any one person, that's what standard deviation is talking about. Standard error is not talking about people, it's talking about samples. Standard error says any one sample mean is predicted to be off on average by 0.65 to the population mean. Higher level of abstraction for the standard error. Standard error is going to define what expected inconsistency is, and whether ours is within the distribution, it's just a little noisy, or whether it's too far away. So we can compute a confidence interval to describe the range of values that are likely to contain the population mean some percentage of the time. That's what it means. I got to be honest with you, confidence intervals to me are not that helpful. I don't like them, but I am beholden to teach them to you because this is something that you will come across and people will ask of us, particularly journal editors. The formula, the ingredients for this, the middle is the estimate. So that means the thing you're putting an interval around. In this case, it's the sample mean, so that goes in the middle. Then plus or minus, and then we have the word critical, which gets filled in with the numbers we had on the previous page. So what is the point on the distribution that this is supposed to come from? That defines where 90% of the cases would fall, or 95%, or 99%. So that's the z value that goes in here. The other number, 0.65, is the standard error. So when you work this out, a 90% confidence interval for the mean is 9.90 to 12.05. So 90% of the time, the population mean is going to be in that interval. 95% of the time, it's going to be in this interval, and 99% of the time, it's going to be in this interval. So wider corresponds to more confident, more inclusive, less likely to be wrong. Okay, let me back up. How are we doing? The correct answer is, because this is the first time you've seen it or the first time you've seen it in a while, and that's fine. Where we're headed with this then is to try and make some sort of up or down decision as to whether our sample mean is too weird, relative to what it's supposed to be. Now, when would you want to do that in life? I can give you an example. How do you know if your sample is representative of the population? That's something that a reviewer could ding you for, right? If you know that X% of your population has some characteristic, X% of the women in academia, or of the faculty in academia are women, X% of the teachers have a master's degree, something like that. Like you have some value that is known from large enough samples or sort of in census data or things like that where you know what it's supposed to be. That's your target, that's your population. So if you want to claim that your sample is representative, then you would hope that in your sample, the same X% of faculty are women, or the same X% of teachers have master's degrees, or something like that. And you want to be able to clarify as to whether yours is off enough to be worrisome or within expected range. So where we're headed next time, I should say, is being able to make that thumbs up, thumbs down decision. In this case, for instance, is 10.98 close enough to 10 that it's okay? Or is this not likely from a different population? And standard error is the magic that allows us to make that distinction. All right. Questions or comments? No. No. They're like emphatic. No, definitely. Do not call on me. I do not have a question.
Want to say, well, thanks for being our cruise director on this stats journey. I don't think it would be much fun otherwise.
Some of it isn't fun. I got to tell you, but some of it is. You know, the parts that I like about this is that, like, when you make something work, like the first time that you type something into SAS and it does what you want it to, and like the numbers pop up, that is a good feeling, right? There's so much that we do there's no end point where it's good enough. Like when you write a paper, you submit a paper, it's like you could rewrite and tweak and revise and add references like for the rest of your life. At some point, you just have to decide the paper is done. Right? When you run analyses like that, there's something satisfying about the program doing exactly what you want, and you have the answers, and that is the answer. So from that perspective, it can be enjoyable in a different way than the rest of the things that you're focusing on. But you are welcome. I'm happy to be your cruise director. Just give it a chance. It will get better. Repetition, practice, and exposure. All right. All right. So go play with the homework system. Start watching some videos if you're bored. Otherwise, I'll see you Thursday. Okay? All right. Peace out, everybody. Take care.